In this pincast, we'll look at multiple springs in a system. To start, we'll start with two springs in parallel. The top one will have a spring constant of K1. The bottom one will have a spring constant of K2. And there is some force being applied to the mass at the end of these two springs. The sum of the forces on this mass then is K1x plus K2x. So both of these springs will be forced to stretched by the same distance x. That means we can define an equivalent spring constant, K parallel, to be the sum of the two individual spring constants. Now if we add a third spring to the mix, the top one will be K1, the middle K2, the bottom K3, a similar mass will be at the end, and a force will be applied on the mass to start the oscillation. Again, all three of these springs will be stretched by the same length x. So our sum of forces is going to be K1x plus K2x plus K3x. If we factor the x out, we'll see that the equivalent spring constant is then K1 plus K2 plus K3. Again, since all springs are stretched by the same distance x, we can use an equivalent K to determine things like energy, frequency, etc. The slightly more complicated problem is to have two springs in series. The first spring on the left will be K1. The second one will have a spring constant of K2. And again, there'll be a mass with a force applied to start the oscillations. In this example, each spring could stretch a different length. It's going to depend on the forces that are applied. So in order to examine this, we need to look at some free body diagrams. For spring 2, there's a force to the right, which is the applied force on the mass to start the oscillation, and an equal but opposite force to the left. That's the force on spring 2 due to spring 1. Now this is not really that different from having a single spring with spring constant K2 attached to the wall on the mass. In that example, we would have the applied force to the right, and then an equal and opposite force to the left. In this case would be the wall. You need to convince yourself that these two examples are the same. If we then assume they are the same, make sure you believe it, then the applied force we'll just call F. It's going to be equal to K2 times X2. Again, X2 is the amount that spring number 2 is stretched. We can rewrite X2 to be equal to F, the force that's applied, divided by K2, the spring constant of the second spring. Similarly, we can do the same for spring 1. Looking at our free body for this, we'll have a force to the right, that's the force due to spring 2, and a force to the left, which is the force of the wall. At equilibrium, these would also be equal. So then the force will be equal to K1 times X1. Then X1 would be equal to the force divided by the spring constant K1. The total extension of both springs together will then be the sum X1 plus X2. Plugging in for those, we'll get the force over K1 plus the force over K2. We can define the equivalent spring constant to be that which is multiplied by the total length that the springs are stretched equals to the force. So if we plug in for the total distance that the springs are stretched, we have the force divided by K1 plus the force divided by K2 quantity times our equivalent spring constant K. Factor out a force, those two cancel. We'll need to divide both sides by that quantity in the square brackets. That gives our equivalent spring constant to be 1 over K1 plus 1 over K2, entire quantity to the negative 1 power. Now we'll add a third spring to this situation. Just like we had before, the distance that each spring will be stretched will be equal to the force divided by that individual spring's spring constant. The total distance will then be the sum of those individual distances. And we can plug in for those distances in terms of the force and the spring constants. Defining our equivalent spring constant K. We can plug in for our total X, of which I've already factored the force out. That force will cancel. Divide both sides by the quantity in the square brackets. And we have our equivalent spring constant for 3 springs in series. Now, you should be able to combine these two ideas of springs in parallel and springs in series to find the equivalent spring constant for a system such as what's popping up right now. 2 springs in series that happen to be in parallel with a third spring. I'll leave it to you to go through and figure that last one out.